Hi, Benedetto.
Oh, hi, Khan. How are you doing?
Good. How's everything?
Pretty good. What about you?
Good. Just from one Zoom meeting to another one. So,
I, I I hear you.
So for those just joining us, we'll begin in just a minute.
sure.
So you are recording our chat between me and Khan.
Yeah, we'll have to edit that out.
Don't say anything compromising, Khan. We
No,
have recorded.
only good things. So, where is this picture? This is
This is in California. It's
California.
one of the many pictures. It's just a deck of pictures, and sometimes I take one or the other.
This is
Uh,
not Camden. So,
No, this is not Camden. You're right. I should put maybe a picture of Camden. Well, it's just then there is the bridge to Philadelphia. So
yeah.
I could put that. There are some nice pictures.
These buildings are not that nice looking either. So.
Sorry, it would be difficult to change on the spot.
No. I mean, I like the traffic. So, I should only look at the traffic. I shouldn't be looking at anything else.
All right, I think we're just about ready to
Yes.
begin. We're at 3:02. Hello, everyone. Thanks for joining us for today's C2 Smart Distinguished Speaker webinar. I'm John Patinos. I'm a project manager here at C2 Smart. This webinar is going to be recorded, as you might have seen, and uploaded to the C2 Smart YouTube channel with all of our other webinars and recorded seminars. If you have any questions for today's speaker, you can feel free and are encouraged to use the Q&A button at the bottom of the screen, and we'll answer your questions live at the end of the webinar. So today, we're really happy to have our distinguished speaker as Professor Benedetto Piccoli. He's the Joseph and Loretta Lopez Chair of Mathematics at Rutgers University, Camden. And this year, I think he was named Vice Chancellor for research there as well. An applied mathematics scholar, Professor Piccoli's research focuses on applying advanced mathematical methods to science, engineering, and health, and his expertise includes mathematical and computational models, ordinary and partial differential equations, control systems, and measure theoretic approaches. He's interested also in control and hybrid systems, social and crowd dynamics, vehicular traffic, network flow, social determinants of health, optimal control for biomedical and biomechanical systems, and much more. Today, he's going to be speaking about autonomous driving and energy efficient traffic smoothing. Before we begin, I can turn it over to C2 Smart Director, Professor Khan Osby, to say a few words.
John, thank you. I was going to ask you that, and thank you very much for doing that. We're really happy to have Benedetto here for this seminar. He actually was at NYU for one semester, I think a few years back, when I was spending more time at CUSP, and he was on his sabbatical, and we spent very good time together. So I've known each other for several years, and I am really glad that he's back, giving us virtually, but a presentation, and hopefully, and I said that a few times last couple of months, he'll to other speakers, he'll hopefully come back in person when we have the vaccine, and we'll have more time and more opportunity to work with him. But I'm also very happy that he's talking about this topic that's becoming quite important. Although this morning we heard that Uber sold their autonomous vehicle units to another company. So from an industry perspective, this is becoming quite interesting, but there's a lot of research to be done. And I think his work on this has been really groundbreaking. So we are really happy to have him here to hear about this very interesting research. And then I would ask all the students, faculty, whoever is on the webinar, ask him questions through chat or after his talk, so that we also have a lively discussion about his work and this exciting and new research. So with that, I leave it to Benedetto to start.
Thank you very much. Thank you, John, for the introduction, and Khan as well. As Khan mentioned, I'm feeling a little bit at home. I spent a semester there 6 months ago. I really had a very nice time. So it's a great pleasure to be back at least virtually to interact with all of you guys, and especially with Khan, who is a good old friend and collaborator. So I want to tell you about autonomous driving, but I will build up a little bit of a story because the way in which we address autonomous driving is with some focus on energy and efficient traffic smoothing. So we want to really try to take advantage of autonomy, both in terms of completely autonomous cars, but as well as maybe some assisted driving devices to improve traffic, because we know, as Khan mentioned, the path towards having AVs deployed in traffic is up and down. It will it will have, I think, few bumps more in the future. But the important point is that autonomy at the vehicle level is anyway increasing. So this, independent from the fact that we will have a given number of AVs immersed in traffic, we will have more and more cars with the capability, at least partial autonomy. So let me start back in 2008, when we were working at what is somehow a precursor from cyber physical system point of view of the current interest in autonomous driving. Back in 2008, the interest was more on monitoring of vehicular traffic. There was this famous mobile sensor experiment by the Alex Bayan group, and was probably the first worldwide example of traffic monitor with probe sensor. They used mobile devices in this experiment to detect the speed profiles along the I-80 in California. And that was a very interesting result. And then using the theory I developed in those years, we worked together at setting up systems that would be able to monitor traffic. Obviously, nowadays, the big guys entered the market since many years, and everyone has on the phone a number of different options for traffic monitoring system. Another characteristics that always accompanied my work was combining engineering problems and collaborations with traffic engineers with mathematical approaches. This is another example of a monitoring project we had back in 2008 in Rome. These are data from mobile devices called clear boxes that were installed by insurance companies. And shortly after, this company called Octo Telematics also came to US around 2010. Anyway, there are very large data set available. And what I want to point out is the big importance of traffic engineers to use the many models they produced over the years. For instance, here in this example, we see a lot of, I hope you see my cursor, a lot of data. So the meaning here is that each dot that you see here represent a speed measure at a given time and position of a car. This refers to the big highways surrounding Rome. And the dot is bigger and lighter if the speed is higher, and the dot is smaller and darker if the speed is lower. So here you see areas where the speed is pretty high, so like, free flow. And then you have a lot of small dots here where queues are forming. And you can notice here, again, this is space and this is time. You can notice some kind of stop and go ways, because here cars are stopped, then accelerate, stop, accelerate, and so on and so forth. And if you want to understand this dynamic of waves, it's really of paramount importance to use models to understand, okay, why this wave moves at this speed and why these other waves, the waves of freeing traffic, moves at that speed. This can be understood using a kinematic model. The most famous is definitely the Lytle-Witham-Richards. That is a first order model that prescribes the conservation of cars through a partial differential equation. Using the theory of partial differential equation, and more precisely the Rankine-Ogonio condition, you can exactly determine what is the expected speed of these waves. And indeed, this is, this theory was confirmed by many traffic experiments and data, and helps a lot, because if you try just to understand data by, let's say, taking your favorite data crunching algorithm or any approach, you will have difficulties in understanding why this phenomenon is happening at this speed and in this way. So models are definitely useful, and it's a leitmotif of my research of using model in data and experiments. So let me make a big jump ahead and talk about the research we started around 2014, but the first significant result we got were in 2016. So all these traffic monitoring projects were interesting, but essentially they pass from the phase of research to the phase of industry nowadays. So what can we do? Can we do something more like controlling traffic with autonomous vehicle? We address one issue that is very well known in traffic, the presence of stop and go waves, as we notice also on those data. This is a clip from Atlanta, but this phenomenon of formation of stop and go waves is really ubiquitous. So you can observe almost anywhere in the world. You will have these waves, also called the traffic phantom jams, stop and go waves, and few other names, that will have a number of effects on traffic, and that will be more precise later. These waves has been very much studied and reproduced both in theory, models, and also in experiment. This is the very famous ICIAM experiment back in, I think, 2006. They placed a number of cars on a ring road that were equispaced and traveling at the same speed. But because of natural oscillations in driving behavior of the different drivers, you will see that some stop and go by waves will form. Like in this video, you see at this point we have a queue forming here. And this queue is indeed traveling backward. So cars you see run around the circle, come to a complete stop, and then reaccelerate. And the point where cars is at stop is really traveling backward in time, exactly as the kinematic shockwave theory would predict. So even in a simple experimental setting, they are very, they show up and they are robust in the sense that they persist. So we wanted to understand what is the impact of these waves and if we can use autonomous vehicles to dissipate them. So the work I'm talking about culminated in a current consortium that we call CIRCLES, and it is comprised of various universities: University of California, Berkeley, Rutgers, Camden, Temple, Arizona, Vanderbilt, government, TDOT, and a growing number of industries, including Toyota, GM, and more are joining. So the main idea of CIRCLES is exactly that, exploring the possibilities of controlling traffic with autonomous vehicles or vehicles with a certain level of autonomy, and producing beneficial effect from energy point of view. Let me mention briefly my main co-PI, Alex Bayen from Berkeley. Jonathan Lin is Berkeley, also is the project manager. Benny Sibor from Temple, Jonathan Sprinkle from Arizona, and Dan Ward from Vanderbilt. On the leadership team, we have also Ken Batts from Toyota and Philip Fries from TDOT. So let me show you what we did in 2006. Back then was a smaller consortium. And what we did is we reproduced exactly the same setting that the Japanese experiment was using. But now, instead of having only human-driven cars, we are gonna have one autonomous car immersed in traffic. Let me stop for a second to talk to you about the meaning of all this information that you see flowing here. So first of all, here, obviously, you see the cars. In the ring road, it was in Tucson, Arizona. The big black arrow indicates the autonomous vehicle. When the arrow is black, the autonomous vehicle is human-driven, so we are not using any control. When it will switch to red, then we are using a control. Down here, you will see a graph in which the solid black line, and then will turn red, represented the speed of the autonomous vehicle. So you see that here, as it's black, is human-driven, so we see oscillation showing up and then clear waves forming. And the information up here, depending on the phase of experiment, will collect various measures like velocity standard deviation, the fuel consumptions in liters per 100 kilometers. We don't use miles per gallon because it's a nonlinear measure, so it's more difficult to understand what it means. The braking events, that means, more than a decrease of more than 1 meter per second over a time horizon of 1 second. So it's they are strong braking. And then the throughput. So let me continue. You see the waves clearly forms. And now we switch on our autonomous vehicle with an algorithm, control algorithm, that essentially try to dissipate waves by targeting a constant traveling speed. Obviously, meanwhile traveling a constant traveling speed, you need to take into account two effects, and not to crash into the car in front, obviously, and not to leave a too big gap that in a multi-lane setting would generate the opportunity of inserting in that gap. So we targeted various autonomous speed, as you can see here, 6.5, 7, 7.5, 8. And you see there is a kind of sweet spot in the sense that when we were at 7.5 meter per second, we kind of reach our best. When we try to go to 8 meter per second, then some oscillation were showing back. And when at the end we switched off autonomy, then you will see that shortly the waves were reappearing and compromising again the performance in terms of traffic efficiency. Let me look a little bit at these numbers. The numbers I want to point out is the comparison between wave starts, so the phase in which we observe waves like in the Japan experiment, and our best result, that is autonomy at targeting the 7.5 meter per second speed. You can see that in terms of velocity standard deviation, so how big differences you see in velocity of car, there is a huge difference. First of all, between no wave and wave, you see it increased a lot, but we were able to reduce up to the 0.64, so around 1/5 of the wave case. But even more interesting, the fuel consumption that jumped at 24.6 liters per 100 kilometers. In our best control setting, we reached 14.1. So with more than 40% spare in fuel consumption. And if you look at braking events that we know are related to safety, under the wave condition, we had 8.5, so 8.5 events per vehicle per kilometer. And we boiled down to 0.12. So we essentially canceled these strong braking events. This 40% fuel consumption was, I have to say, even above our best hopes, in the sense that you do perform model experiment simulations, but when you go to the reality, there are a number of technological difficulties. So you may expect that to go down, and we were able to keep to a 40% that is pretty striking. So that's why this convinced us to go ahead and do something more. But let me point out one thing, because comparison between autonomous vehicles and vehicles with autonomy. Here we use a control algorithm that were not too difficult, in the sense that we were targeting some travel speed like 7.5 meters per second. We were being careful about being safe, not leaving a too big gap. But the control was pretty standard, using ideas from stabilization and PID controls. But was carefully designed and tested. So the question is, the technology we use is not very different from the autonomous car cruise controls that are, or automatic cruise control that are currently available on many cars. So the idea would be, the question would be, is that enough to produce a result of this type, like stabilize traffic and reduce waves and fuel consumption and braking events? So we address also this question looking at commercially available adaptive cruise control. And the matter of fact is that, you see, these cruise controls are not designed to dissipate wave. They are designed mostly for safety and keeping the speed that is at will of the driver. So in this case, let me stop for a second. We are still in Arizona, and we got 8 cars identical, of the same make and the same model, and with the same ACC system, so to have uniformity. And we drove a platoon of 8 cars. The first car is human driven, and the other cars do have the ACC system activated. So we asked the human driven car to perform a slowdown in speed. And you will see the first car will start to slow down. Sorry, I forgot to say, but here on the right, as you can imagine, we are representing the speed of all vehicles during the experiment time. The blue line is the last vehicle in the platoon, and all the other red lines are the intermediate vehicle, including the human-driven one. So this line means that you see the human-driven vehicle is adjusting to a lower speed. Notice that in this first part of the experiment, we were in perfect platooning because all the cars were driving at exactly the same speed of 50 miles per hour. So you see the first car, the human-driven, decrease its speed and then it adjusts with another ACC. Then you see the second car does the same, but you see the dip is bigger and bigger and bigger as we move down along the platoon. And what happens for the last car, and you can see also in the movie, the last car really stops and will move on a side. And the reason is that the dip was so big after 8 cars that indeed at 25 miles per hour, the ACC for safety reason disengages. And so the car becomes human driven. And in that case, it parked on a side, not to be any more part of the experiment. So this experiment showed that indeed the automatic adaptive cruise control, are not designed to smooth waves and are so-called string unstable. So there is a mathematical constant of string stability that essentially means if there is an oscillation, your ACC will tend to smooth this oscillation. And you see in this case is experimentally proven, and we proved also with the models that if the first car produces some oscillation, the second will amplify and so on and so forth. So at the end, we obtain this disengagement of the ACC, and this corresponds to say that we cannot expect this mechanism to indeed be string stable and produce wave dissipation, but rather they would increase. Now, there were some experiments performed also by some car producer that showed that despite the fact that they're string unstable, they still amplify waves less than humans, but still they are far from the ideal situation like the one that we showed in the experiment of 2016, in which we can completely dissipate waves, and obviously those controls render the system string stable. Now, with this consortium, we are aiming at a very challenging and ambitious goal, the one of performing an experiment on a true highway. We identified our field operational test as the I-24 in the Nashville area. And what you can see here are images, are videos of some cameras that we mounted. I will talk more specifically in the next slides. And there is an identification algorithm that identifies cars, trucks, SUVs, and so on and so forth. So we aim at 2022 to have this experiment deployed. We are performing a number of different experiments, a number of different sites with the smaller numbers. And our aim would be to use 100 AVs and have a full operational test on I-24. As you can imagine, there are a number of challenges, obstacles, but we are progressing towards that goal. And we still hope that by 2022, we are going to be able to do that. Just one maybe anecdote. We developed a lot of theory, a lot of results, a lot of simulations. And one, for instance, roadblock that we had is that this year we expected to collect a lot of information from onboard sensors about traffic waves. And due to COVID, there is much less traffic. So we have much less data about the traffic waves because they show up much less. So there are some challenge and delays, but the program, the project is up and running. So we hope still for 2022 to be able to achieve that goal. So let me now speak a little bit more, because I think from engineering point of view, it's interesting about this simulation testbed. These are the type of cameras we use. So in collaboration with TDOT, Vanderbilt mounted over 110 or 100 feet pole this system of cameras that were existing camera of TDOT plus 8 new 4K resolution cameras. And I can show you here the event in which they raised the first 3 poles that happened last summer, so a few months ago. And well, it's pretty impressive. These are 100 feet poles you see that are raised. Obviously, this is a time lapse, and you will see the poles are raised up. Now, just to give you an idea of what we will use for, well, obviously we want to run with our autonomous vehicle, regularize traffic, but we need to estimate the advantage of regularizing traffic. And while in the Arizona experiment, we were able to use onboard technology and measure directly the fuel consumption, in this case, we will need to estimate the fuel consumption with advanced camera images for the cars that are not involved in the experiment, while in the Arizona experiment we had all the technology on board and measuring directly. As a byproduct, this Tennessee testbed will generate a flow of data that is probably unprecedented. Let me just recall some of the famous data sources. Well, first and foremost, the very famous NGSIM, on which was used very extensively by many researchers to perform analysis of the data. As you know, it was in California. They had camera images from the I-80, and they had around 1,100 vehicles miles traveled. Now, another example is 2018, the ID German project, where they used drones and they taped and cameras as well, and they have 25,000 vehicles miles traveled. So we do hope that when the whole system will be up in 2021, we should have around 16 million of vehicles miles traveled per year. So you can see the amount of data is going to be just amazingly big. We are, especially the Vanderbilt partner, is chasing funds to increase the computational capability, because even just the video elaboration of all this data is pretty challenging. But since I'm a mathematician, let me spend some time to talk about some details of the math approaches that are using, because what I like very much of this project and consortium is also the fact that it spans very different research areas and needs and capabilities. For instance, the Berkeley group performed a lot of simulations in the flow system, and they work a lot on AI algorithms. My group works more on the model-based control algorithm and modeling in general. The Temple group works a lot of energy, because obviously we need to have reliable energy models to estimate what will be the experiment result. And Toyota is a great partner in that sense. And the group in Vanderbilt, as you saw, is dealing with heavy engineering projects, installing and the cameras, videos, and the group at Arizona, they have all the knowledge about autonomous vehicles. They have a CAT vehicle, and they have a long-standing expertise on how to build up autonomous vehicle devices and so on and so forth. So let me talk a little bit more about my part in this project. What I like is that this team is very interactive. So we meet, I would say, at least 3 times a week. And we do interact. We have around 50 students altogether between postdocs, PhD, and so on. And the interactions are very intense. So let me now deep dive a little bit on the models that we are using to design our controls. So first of all, let me remind that in traffic, there are a lot of different models and scales at which we tend to represent traffic. The most classical one are obviously the microscopic, in which we identify position and we identify the system by exploring position and speed of each car. And there are a lot of microscopic models, including follow the leader type, like this equation here. You see the derivative of the speed is given by the difference between the speed of a vehicle ahead, the I vehicle, divided by the head weight, that is the difference in position. This is kind of the minimal model. Obviously, there are many other, like the Gibbs, the Bando, and there are a few names, and we use a lot of these models. We complemented these models with a hybrid part because we consider lane changing. And lane changing model, I will not have the time to revise, but there are many, many people that work on that, both at microscopic and microscopic level. Talking of which, the macroscopic level is, I would say, the opposite scale, at which you look far away the traffic, and rather than assuming you distinguish every car, you look at the global, the cumulative density if you want. So you have some quantity that depends on space and time. If you do this macroscopic approach, then it's very simple to obtain an evolution equation just by prescribing conservation of cars. As you know, the integral between A and B of your function rho represent the number of cars in this stretch of road, and the derivative is given just by the difference of the flows. Positive what enters in A, negative what exits in B. And if you do so with a little bit of simple algebraic manipulation, you obtain what is known as a conservation laws. And assuming that F depends the flow that is equal density times speed depends just on rho, or that the speed depends just on rho, you obtain the very famous Lytle-Witham-Richards model. All this is pretty well known, I would say, in the traffic community at the different scales, but we are using an approach that is probably a little bit less common. So first of all, let me remind that many of these models were also inspired by gas dynamics, in which there is also another scale that you typically consider, the so-called mesoscopic scale, in which you write the probability distribution function of the typical vehicle to be positioned in a certain, at a certain time in a certain position with a certain speed. Now, there are a lot of results connecting these different scales. Obviously, this is not a novelty. This goes back to Prigogine, Paveri-Fontana, and many others that proposed the mesoscopic model for traffic. But what is interesting is that a little bit more of modern language. Now people saw that connecting the scale is possible by using a unifying language with a nonlinear transport equation in terms of measures. So indeed, what happens is that you can represent, paying the price of more mathematical abstraction, you can represent different scale of the model, or sometimes even the different scales together in a multi-scale approach by writing nonlinear transport equations that are PDEs that essentially encompass these classes of PDEs. Let me remind quickly for those that are maybe a little bit less familiar with what is a measure. One of the most famous is the Dirac delta, and you could assume that is essentially a formal limit of functions that have always the same mass and whose domain restricts. You see, like in this picture, these functions, they all have the same mass, the same integral, but you restrict the domain, so it tends somehow to infinity at this point. Then the formal limit sometimes also in physics indicated this way, to say the function is always zero, but there is a peak of mass here. To understand mathematically, the correct way of thinking to a measure is really as an operator over function. So it's something that acts on function, evaluating it at a point, for instance, the Dirac delta. With this language, it's very natural to rewrite the microscopic model with a little bit of mathematical abstraction using interaction kernel. So take your favorite model, Bando, follow the leader, whatever. You can rewrite that with the convolution operator, where this convolution acts on what is called the empirical measure. Now, the empirical measure is nothing but the following. You take all your cars that are at position, say you have the car, the ith car at position xi via xi of t vi of t, and instead of having the car, you place there a Dirac delta. So it's like if there would be a mass concentrated at the car position. If you do so, this is a measure, and having the measure satisfying this equation, or even better, this partial differential equation, is exactly as the position of the cars satisfying the corresponding ODE. So this is a language that allows automatically to reinterpret ODEs as a measure problems, and to reinterpret also PDs in the same way. Not only that, but you see these two scales are connected. You can pass to the limit from one to the other. And indeed, more than that, they are essentially the same equation. Just if you look at the microscopic and macroscopic setting, you will see them just slightly differently. Now, there is an enormous literature for passing to the hydrodynamic limit. It's very famous, the so-called propagation of chaos approach. It goes back to Kach. While the more formal limit and mesoscopic scale was started by Dobroshin and many other, and used mostly the Wasserstein distance. But let me skip a bit of technicalities and tell you just that what happens if we insert control, because our aim is really controlling traffic. That's what we aim to. So what happens if I consider my favorite ODEs, but insert a control terms that is an acceleration? Can I pass to the limit? Well, there are conditions to pass to limit under this control, but the big problem is that if I pass to limit without care, what happens is that the limit will appear as a new term, but in measured language theory, this can be very complicated, because this measure in measured language theory could be orthogonal to your measure solution. So essentially, your limit control will have no effect on your solution. One of my collaborators like to say the following. It's like if you would like to control a reader with 1 million or 1 billion toothpicks. You know, in principle, you are inserting a lot of mass into the system to control, but you see, these toothpicks will have so little effect locally that their global effect are going to be negligible. There are a number of ways to bypass this type of difficulties, and let me mention probably one or two. The first one is control by leaders. So what we do is the following. We split the population of cars into two groups. A first group, small one, that corresponds, say, to small m cars, would be the one with autonomy or completely autonomous. And we assume that these cars can be controlled. So they have a control term here. We assume that the rest of the traffic, so a big n number of cars, is not controlled. So they satisfy the same equation, but without the control. Now, what is indicated here by mu n and mu m represent the empirical measure corresponding to the first m cars for mu m and the rest for the following. This is just to say that you see the control cars interact also with the non-control one and vice versa. So if we do so, we can pass to the limit, but passing just on the number of human-driven cars. If we do so, we are keeping some control ODEs for our control cars, and the bulk traffic evolution will tend to a PD of the type I indicated before. Now, the interesting point here, you see, is that the control, we stick to the microscopically represented part, while the macroscopically represented one, not control, we just satisfy an equation of the previous type. And this is really a completely multi-scale model, because we have control ODs and not control PDE that interact. You see here the interaction, because this mu appearing here represents that, and this mu m represents the empirical measure corresponding to these cards. So it's completely coupled. For this type of systems, we can consider optimal control problems or even stabilization problems. So stabilization would be, well, we wanted to drive the traffic to a stable solution in which all cars drive at the same speed, like we did in the ring road experiment, or we can have a more complicated functionals in which we can try to address directly the fuel consumption. And obviously, we usually penalize the control. Now, a little technicality, but this is called typically an L1, L2 norm. And this norm pushes for sparsity. So usually controls that optimize this type of functional will tend to act just one car at a time. That could be an advantage, or a small number. Now, from mathematical point of view, what we can achieve is a big result of gamma convergence of one functional to the other. So this is a bit technical language, but essentially what it means is that optimal controls for the discrete case will converge to optimal control for the continuous case. So you can use this result in two ways. You can either try to design control at microscopic scale and then use a macroscopic. So assuming that if your control is well designed, will possibly be not much depending on n, or vice versa, you can try to design control at macroscopic level and then try to project better microscopic one. Let me probably mention just one more approach. There are a few more, but this result, for those that are curious, are in this paper that goes back to 2014, and now we are using in the traffic setting. This was a general result for more general systems. Other approaches that we are using are also multi-scale. There is the Delle Monache-Goatin model. That is a model for moving bottlenecks or AVs immersed in traffic. In this case, we have the LWR model, a single AV driving in traffic with its own speed, depending also on density. And there is a flux point constraint. So there is a lot of theory developed for this model, and we are using this model. You see, this is also multi-scale because you consider bulk traffic and a single ODE for one AV, but you can immerse many of them. And indeed, we are using this model in a generalized setting in which we have multiple autonomous cars and possibly even multiple lanes. And for lane changing, we use some of the known mechanism. In particular, there is some safety constraint to operate a lane change and some incentive. So cars will perform a lane change only if it is convenient enough. We do add usually a third criterion that is called cool down. So we assume that drivers will not perform a lane change short time after having performed another lane change. And we use a similar constraint also on the control that we are implementing. I have few more slides, but I think that I gave enough, I hope, a good idea of the overall project. So rather than getting into more details, I would conclude here and open to questions. Thank you very much.
Thank you, Benedetto. This is very nice. So let me see if there's are there any questions on the chat box? Let's see. I have few, so I can start asking few questions. Simple. So the tendency test bed, how how many miles is it a mile and a half? I mean, maybe I missed that.
No, you didn't miss. On purpose, I didn't say. No, I'm joking. So the current situation is
secret. Yeah.
it's a secret. No. So the real situation, as you can imagine, the installation of these poles is a big engineering operational problem. So for the moment, we have around a mile and a half instrumented. I showed you the 3 big poles that were raised, and there was another pole that was up and running before that. Now Tennessee is doing a fantastic job. Vanderbilt and the group of Denmark are working the TDOT to get more poles up, and they hope to have a few more in probably in mid 2021. The exact number, as you can imagine, depends on budget, depends on various constraints. We will have at the minimum, I would say, currently we have more than 1 mile instrumented, and the overall stretch is around 15 miles. I doubt that we will have all that instrumented by 2022. We will have part of that. We are projecting also using some alternative method to extend, like if we have, say, 2 miles, 2.5 miles that are instrumented, we could maybe reach 5 miles with drones. So there are various solutions we are thinking, but I would say more than 1 mile is already instrumented. So that's really the minimum, but we will have more than that.
So you're getting data from that 1 mile? Is that?
The data are already flowing from that mile. And in 2021, we expect to have a larger stretch instrumented. And by 2022, I cannot predict exactly. The overall stretch in which the experiment will be performed is around 15 miles.
I see.
And currently, more than 1 is instrumented. So,
I mean, of course, one of the things to extract that data, no? I mean, you mentioned that they will need additional. I mean, I remember for NGSIM, which is 45-minute, I think, 50-minute data, because I was part of the kind of monitoring group. So I kind of exposed my age. It was many years ago, but and it was so expensive to extract that data for 45 minutes for, I mean, short range. Obviously, technology changed, but
yeah. No,
yes.
I mean, you are absolutely right. So first of all, it's true. Technology changed a lot. 14 years passed by, and especially the video algorithms now are much faster. Even those ones many are based on AI. But the volume of data is so big that there are two comments probably to put there. First of all, they are constructing a whole small building where to host some computer capabilities to elaborate on the spot all the flow of data that are coming. But most likely they will not be able to store the video data. They will already transform on the go onto other formats and then dump the video data and keep the elaborated format, because the video data itself is so big that is almost unstorable.
So for the model, so this is interesting, and we can talk more about this because this is, of course, the funding. It's also interesting for this kind of thing because I mean, it just probably you're talking about millions of dollars. So
Yeah, all together, I think we raised up to now 6-7 millions, but there are more flowing in. Obviously, bigger group of people and all that technology requires a consistent amount of money. Yeah.
So for the model, you said the individual vehicle in this combined model, the individual vehicle, the OD is for one vehicle. But I mean, from our work, we observed that the location of that vehicle within the traffic also makes difference. No? So are you assuming that that vehicle is always the leading vehicle, or is it somewhere in the middle of the traffic? I mean, how do you
yeah, so this in this specific model here, I don't know, Khan, if you were referring to this one, this specific one that mixed OD PDE, the vehicle is supposed to be in the middle of traffic, in the middle.
Always in the middle, okay.
Yeah, exactly in the middle. In this other approach that is more starting from microscopic, going to macroscopic, here really the vehicle could be almost anywhere. And you see, we have a group of vehicles here. So since here we start from microscopic, we are gonna be, we can place essentially anywhere. Now, I think you refer also to the fact of what you can do with the control. Clearly, the controlling the leading vehicle is very different than controlling vehicle in the middle. But we wanna perform some control on the highway, so we will have most likely, like the Century experiment, cars driving through the stretch of road, then exiting and re-entering back. So we cannot assume that we are controlling via leading vehicle. This will be immersed into the bulk traffic.
So I mean, is there so the claim is that even one vehicle will be enough?
No, I'm not saying that much. So in the ring road experiment, one vehicle out of 21 was enough to control. So say around 5% penetration.
Okay.
And that's the type, I'm not sure we can reach 5% penetration during the experiment we are planning for 2022. It will depend on the volume of traffic, time of the day, and also the number of cars that finally we will be able to have and deploy. But as you know, there are a number of results, theoretical, both for traffic monitoring and control, that talk about something between 2 and 5% you should be able already to have an effect on traffic. So what we are aiming is to design an experiment in which we can reach that type of penetration between 2 and 5%.
Okay. And that's assuming vehicles are all the same type of vehicles. So I mean, because if you have trucks versus cars, that might make a difference. No? So...
yeah, unfortunately, obviously, our idea is to perform the experiment live on the I-24 with real traffic. So we will have we will have control on our fleet. We will not have control on the bulk traffic. So the bulk traffic will most likely include also.
So I mean, that's another question, and I'm gonna stop. I'll see if there are other questions. But so you talk about optimal control. I mean, in real traffic, you have to do feedback control. No, so you cannot. Just have the optimal trajectory and assume that will remain the same as for the reasons you mentioned, because you don't have control on the rest of the traffic. So how does this? I mean,
no, that's as usual, Khan. This is a key question. You are getting to the point. So all the controls we performed in Arizona and in the Arizona experiment were stabilizing type controls.
Mm-hmm.
So controls that are designed aiming at trying to drive the group to travel at the same speed.
Mm-hmm.
Now, because of the ring road confined situation, that was working very well. But if you go in a multi-lane setting, if you leave too much of a headway, someone could cut you in, and so on and so forth. So what we are designing is first longitudinal control, in which we will try to see the effect of a single AV, say, positioned in a middle lane of a 3-lane situation. And in ring roads, again, known in practice, but in theoretical experiment, things are still going pretty well. What we will use the optimal control approach is mostly to design the lane changing part. So essentially, well, in simplified terms, then obviously all the machinery is a bit more complicated. But as you can imagine, you may use your longitudinal control to stabilize your lane. And then when you see that one nearby lane is much less stable, when it's safe, operate a lane changing. Said in these terms sounds like a little bit trivial, but one of the key points is when to decide to perform a lane changing. Should we expect that your lane is completely stable and the other one is completely, set off with big waves, or what's the best moment? That's a question more like optimal control and that's what we are specifically studying. But within a single lane, I would say that the longitudinal control is mostly still designed in terms of with a stabilization idea in mind.
But the lane changing is not explicit in your control. No, so it'll be something almost like an engineering. I mean, so.
Oh, well, whatever we do in theory, then we have a complete pipeline. What I mean is that we do perform usually simulation. When I say in theory, it means that we, construct idealized models of a stretch of highways or ring roads and so on. Once we perform that, then we pass to a dashboard in which we have some sites with a calibrated model in flow that uses Sumo or IMSUN or other microsimulator. And then we run through those models and we see what's working and what's not working. Okay. And then we start to doing parameter optimization following that. Then there are a few other steps before going to the car level. And that's what we did also for the Arizona. That's why it was also pretty, it's a long process because, as you can imagine, you design, for instance, your control as an acceleration control. And then when you go to the car level, you realize that some of the robots controlling the car accepts a velocity profile and not an acceleration one. That's just one of the hurdle that you find down the road. But we do believe that this model with optimal control can give some ideas on designing the lane changing mechanism that then will go through a number of, the whole pipeline before being deployed onto the cars. Right. And in any case, we will be very, very careful about
Sure.
because the longitudinal control is already risky, but the automatic lane changing even more. But you see, we are keeping open the possibility of having human operated lane changing suggested by the algorithm.
Yeah, I mean that there different approaches. One is like, as you said, kind of opportunistic lane changing. So you find, based on the minimum opening, you find, the decision for lane changing. But there are also some people looking at predictive lane changing. Basically, they do the path planning. Basically, they plan the whole path of lane changing on the fly, and then follow that path and update that path in real time, which is much more complicated. Probably it's not how human beings do, but it's a robot. So, and you can have a big computer doing that kind of a probabilistic path planning. So you just go with the most likely path and then update that path based on what's happening around you, which is much more difficult problem, I guess.
Oh yeah, no, absolutely. And for the moment, we are using, you see, a pretty simplified version of the lane changing condition, like the one here now on the screen. And this is the first, say, attempt to combine with these more advanced models. But I completely agree with you. There is a lot of very interesting activity on how to perform the lane change, the whole path of planning, and we are not yet addressing that aspect. Would bring even more complication to that. And as I told you, we are not yet sure if we will end up doing an automated lane changing or human operated, suggested by the algorithm.
I think that I see a few questions here. So
Yeah, we have a
John,
couple.
maybe you wanna?
Sure, yeah. So we have a few more minutes, so we'll pack a few questions in the remaining time. But the first one comes from your colleague, actually, at Rutgers, Professor Hani Nassif. He asks, since autonomous trucks are becoming more popular for freight companies, and knowing that trucks might be posing additional safety concerns, would these models that you've talked about today need to be modified so they are applicable to autonomous trucks?
To autonomous trucks?
Trucks, yeah.
Yeah, so to tell this is a very interesting question. To tell the truth, you see, we are aiming at designing an experiment in which we will prove that it's possible to control traffic. And we will not even enter the problem of doing that with a truck. We will use sedan or say more regular cars to do that, like we did in the Arizona experiment. That's a very interesting and active research field, but we are somehow tangential to that. Our idea is we want to prove that with some level of autonomous driving, you will be able to benefit the overall traffic in terms of fuel consumption. The truck problem is somehow, I would say, I wouldn't say orthogonal because it's obviously connected, but there is, at least to my knowledge, a lot of interesting research going on, for instance, in platooning of trucks, automatic platooning, and it's kind of tangential to that direction. We will try to control the traffic with a small number, but not trucks.
Okay, so let me make sure I get this question conveyed correctly. Can you, this is from Danny Gal, can you elaborate a little bit more about your field tests, especially with regard to the communication tech that was used and any performance evaluation plan that you're using, especially as you expand to 100 AVs in 2022?
Yeah, so both is the communication and the plan. So in the Arizona experiment, for instance, I showed you just one example, but as you can imagine, we performed batteries of experiments and different controls. And among them, one that I think was interesting, we did continue to use the human driver, but with the communication on try to drive at a certain speed. The driver was a trained driver, so not any driver. But we told the driver, while keeping safety, try to target this speed. And we obtained pretty interesting results. That was, we reduced by around 20% the fuel consumption. So around half of the advantage. But it was interesting because it was, if you want, a first communication experiment. Once you set up such a big thing, you are not going to do, obviously, just one experiment. We are going to do multiple, and we are going to test different communication possibilities. But we are not very active in terms of V2V protocols. What we will probably explore is this type of communication to the driver or communication to the car, because through the monitoring system at Pulse, we can detect, for instance, downstream traffic problems and communicate in real time to some of the cars. Since the number of cars we are going to use will be limited to 100, we are going to have some challenges there, but it's not going to be a major communication experiment. That's not going to be. For what concerns the evaluation of the experimental result, the test bed is the key point, right? We are going to have all these poles with high resolution cameras, and we are already testing the performance of evaluating the fuel consumption just with the trajectory of the construction from the cameras compared with fuel consumption model that are provided in collaboration with Toyota, and obviously with the onboard measurement. So we are going to compare that. As we know, unfortunately, fuel consumption, there are many models, but they strongly depend on the vehicle characteristics. Now, many of these video algorithms will allow us also to identify with a reasonable precision make, model, and so get an estimate of the fuel consumption. It could be a bit refined. But let me say that my philosophical point of view from that angle is that I doubt that it's even possible to have accurate fuel consumption estimate for a single vehicle. But what we are aiming here is to show that the overall effect system-wide will be big. I don't think we will reach the 40% like the Arizona experiment, but if we can prove that in average with a reliable estimate, we can spare, say, 10, 15%, that's going to be already a big impact, and that's what we are aiming at.
Okay, I got one last question here. Let's see if I get this one right from Mladen, and feel free to retype it if I get it wrong. But so what do you think about this scenario, which is having a cluster of controlled CAVs control multiple lanes to act as like a multiple lane moving bottleneck?
That's exactly what we will do in the experiment and what you are doing in the model. Maybe, I'm sorry, I was not that clear, but I didn't spend too much time in the details here. But on the I-24, we are going to have 3 lanes, and we are going to deploy cars that will occupy one of the 3 lanes. Most likely, we will stagger them by lanes and obviously by entry time. What we are designing is at the same time longitudinal control. That will be the control that will be active as long as one car stays in the AV stays in that lane. And then, as Khan asked, the more optimal control approach to design some lane changing mechanism at need. Now, the simplest scenarios would be the scenario in which, you just give an entry point to cars, autonomous cars, and you assign a given lane. So you see, you deploy one on lane 1, and you are going to keep it for the whole experiment until the car exit. That could be an experiment of, a first level experiment. The second level would be allowing the autonomous car to do lane changing during the experiment. So in that 15 miles of highway. And for that, we are using more optimal control approach. Again, a word of care, as Khan also mentioned, there is a very active research line on automatically operating the lane changer, but this is obviously an extremely difficult problem and delicate, and the safety is a big issue there. So we didn't yet make the final determination of how frequently and in which way we will operate the lane changing with the AV to control traffic. In theory, we are running algorithm, experiment, and so on, but in practice, we will need to make a decision depending on safety and also with other partners like TDOT, if to operate human-driven lane, human operated lane changing or at all.
Okay, so that's that wraps up. Thanks for discussing this cutting edge research with us. I can't wait to get in one of these new cruise control cars with energy efficient traffic smoothing. Just a quick note before I formally thank our speaker today. If you enjoyed this webinar, definitely follow C2 Smart on Twitter, join our LinkedIn group and mailing list. We're going to have Rutgers professor Hani Nassif on for our next webinar on December 15th, updating us on the state of his Way in Motion project and autonomous enforcement on the BQE. Vice Chancellor Benedetto Piccoli, thank you so much for joining us today. Like Dr. Osby said, we hope to see you back here on the C2 Smart stage.
I'm looking forward to. Thank you very much.
Thank you, Benedetto. Thank you for a great presentation. So,
thank you.
Have a nice day. Bye-bye.
Take care.
You too. Bye-bye.
Bye-bye.